Okay, in my part, I will introduce you some basic idea about plane wave-based method. And as Dr. Pusana said at the beginning, we try to, with the time constraint, we have to make it simple, and it may be boring for the expert, but it's good for student. So this is the outline of my part. So I give you some idea about plane wave-based DFT and the predict system that you need to know before using this method. And for the plane wave, I will give you some idea about pseudo potential and also the POW method and the key points about the computation that used in this plane wave method. Besides WASP package, there are many plane wave-based DFT codes that provide nowadays. Here is an example of other code that use plane wave, such as the app init and quantum espresso, castape, and siesta. And there are other software also. And for the student who want to know how to start, you have to read more about the solid-state physics and about the predict system. And you can also read the textbook about computational chemistry and materials and physics. And you can also go to the website. In WASP website, they provide a useful information and also the tutorial and example and good manual. And also, there are lots of stuff on YouTube, so you can go and check it. And what is the plane wave-based DFT? In this method, it just express a plane wave basis set in form of plane wave. And also, charge density and also the local potential are expressed in terms of plane wave. And what is it good for? It's good for the extended system, which has the periodic boundary condition. So you can apply this to study the crystal or bulk structure and surface or slab structure and also molecule in the box within the periodic boundary condition. Let's come back to the periodic system. It's good for a student. The periodic system can be described by the repeating unit, the smallest cell. So if you extend this repeating unit in the X, Y, and Z, you get like the large or the extended system. And here is an example of the BCC crystal. So if you extend in the X and Z direction, you get the bulk structure of BCC crystal structure. And here is the example of periodic system. So as I said that plane wave can calculate the crystal, molecule, and also surface. Here is an example of the bulk TiO2. When you have the cell of the primitive cell of the TiO2, when you extend it, you can get the structure of bulk TiO2. So if you calculate this, you will know the whole property of the whole system. Or you can calculate the molecule in the box. When you put molecule in the periodic in the box that large enough that if the dimension of the cell is large enough to prevent the interaction between the molecule and its replica, you get the property of the isolate molecule. And here is an example of the surface or slab system. Here's example of TiO2 101 surface. So one thing that important is you have to have the large space between the surface. This replica. So you will get the property of this surface. So as you seeing in this slide, in all three systems, you need to have the box of to specify the periodic boundary condition. So in real space, you can construct the box of the cell by lattice vector in 3D. This is the real space. So for example, in this figure, here is the primitive cell of FCC crystal. So if you construct the primitive cell by A1, A2, and A3 lattice vector, you can get the structure of the FCC in real space. And when you do a Fourier transform from real space, you can get the reciprocal lattice vector of structure. Because of plane wave, they use the advantage of FFT or Fourier transform to calculate. So it needs to know that a little bit about the Fourier transform of the lattice vector. So one thing that the student need to know is the dimension in reciprocal space are the inverse of the dimension in real space. So you can go to the textbook, solid state textbook, and see how to derive. Here is an example of FCC lattice in real space, but in reciprocal space, it will be like this. And the lattice constant of the cell is A in real space, but it will be 4 pi over A in reciprocal space. So the smaller size in the real space will be bigger size in the reciprocal space, and vice versa. And in reciprocal space, when we calculate the property in the Boolean zone, we can get the whole property of the system. And the irreducible Boolean zone represents the smallest region that represent the Boolean zone and all the whole system. Here is an example of the Boolean zone of the FCC, and here is the IBC of the hexagonal lattice. So if you calculate and have the property of in this region, you will know the whole property of the whole system. And that's a basic idea about the periodic boundary condition and system. And come to the plane wave method. You might have a question, what is the plane wave method? According to Dr. Pusna's session, she represents this Concham equation. And for the for the basis set, the wave function of single electron wave function, we can expand wave function in a basis set. So this basis set can be represented in form of localized set, like you use in Gaussian or atomic orbitals. And in plane wave, we use the localized set to represent the basis set of the electron wave function. And from the Bloch theorem that apply for the periodic system, the plane wave, the electron wave function can be represented by this form, the plane wave part and the periodic function part. So the periodic function have to specify that when you do the translational operation, it doesn't change the property of the basis set. And also, all periodic functions like beside wave function, the charge density and potential also represented in form of plane wave also. And ideally, there are infinite number of plane waves, but for the reality, when we do calculation, we have to specify the number of plane waves because we have to wait about the accuracy and computational time. So this one is the important keywords that you need to know, the cutoff energy. This one is is the maximum kinetic energy that used to specify the plane wave that allow in the calculation. So if the plane wave that have the higher kinetic energy than this value, it won't include in the calculation. So in reciprocal space, it will show as the cutoff lattice vector, the vector, G vector. And in plane wave, they do the Fourier transform, and we'll do calculation in real space and reciprocal space. So if you consider this is the example of the wave function in the real space, and this plane wave is included in the calculation because it located inside this G cut. But for the plane wave that have a higher kinetic energy located outside this G cut off G value, it won't include in the calculation. So this is the parameter that you need to test before doing calculation. For each system, it might require different value. And come to the potential part. Like Dr. Pusna said that the potential is used to describe the nuclei electron and electron-electron interaction. And in WASP, there are three potential that provide, such as this norm-conserving pseudo-potential and ultra-soft pseudo-potential, and the projector augmented wave. This one is the most recently method that is well-known method that we usually use for now. And all three potential are developed from the frozen core method approach. So as you know that, we know that the valence electron is important in the bonding or the property of the system. So in this method, the frozen core method, we just focusing on the valence electron, and for the inner shell electron, we just fix it and call it like core electron. And we represent this core electron as a pseudo wave function potential. So here is an idea of the pseudo potential for here. If you specify the cutoff energy, cutoff radius, so on the left-hand side represent the wave function of the core electron wave function. So you will see the node. There is fluctuated wave function here, and we assume that the inner core electron doesn't involve in the interaction. So we treat this instead of treat it as the exact functional. We replace this by pseudo wave function, by one pseudo wave function, and for the wave function of the valence electron, we treat it like exact function, and also we apply it like for the potential part and the wave function part. For example, for aluminum, the valence electron is a 3s and 3p that we treat as the exact wave function. And for the rest, we treat as a core electron wave function by a pseudo wave function. And for the projector augmented wave function, it is a combination of the pseudo potential method and all electron method. They also calculate in 3 parts, and this method use the pseudo calculation and replace the all electron on site by removing this pseudo on site, but we treat the all electron on site. And this one is claimed as good as the all electron methods, and it is well-known method now. These are the keywords that you need to know before doing WASP about its computation. For the plane wave, it has advantage of using FFT to transform back and forth between real space and reciprocal space. And we have to sampling or calculate the Boolean zone that I showed you at the beginning. And we have to do the sampling or K-point sampling. So this one, the K-point sampling, also important. If you want to get more accuracy, you have to put more K-point mesh to sampling your system. And also the energy cutoff that specify the number of plane waves that you use in your calculation. The higher energy cutoff, the higher accuracy, but you have to wait between accuracy and computational time. And also, you have to look at the relaxation algorithm. Here is an example of the first Boolean zone sampling. So it's like, if you have more K-point mesh, you get more smooth and the real property. But you have to be careful because if you have the longer size in real space, like I said before, there's a shorter dimension in the K space, in the reciprocal space. So if you want to calculate the bulk structure, which is small, you have to increase number of K points. But if you have the large system in real space, you can reduce the K point because it has smaller size in reciprocal space. Here is the 2D figure of how to sampling a K point. Actually, the WASP will sampling the K point mesh will generate K point automatically. But it's good to know that when you specify, like, for example, here is the example of when you choose K point of 4 by 4, it will generate K point, 16 K point, 4 point along the B1 and 4 point along B2. And here it generates the K space around the gamma point. If this one is the gamma point, you have to be careful about the number of K points. So you have to test the convergence of the calculation with respect to the K point also. You can make a choice that you can, when you use 5 by 5, you can get one K point at the gamma point. So this is the example of sampling in Boolean zone. And as I said, if we use denser mesh, the more Fourier component will be included in calculation and higher accuracy, but it spends longer time. And you have to be careful when you calculate the metal system because of the occupancy. It is step function. So you have to need a denser mesh for the metal system. So you can go in detail and see the example of the calculation from WASP website. And here is a self-consistency cycle, like Dr. Pusana presented before. But I want to remind you that we call this self-consistency cycle as an electronic step loop. It's for optimization of the electron. But when the electronic step is converged, it will move the ion in the lattice. So this this bigger cycle called ionic step relaxation. So for the summary, advantages of the plane wave method. So it can apply in many systems, and it can use the FFT to make the computation more efficient, and you can control the accuracy of the system by K point and in cut off energy, and it's easy to control convergence. However, there are limitations also because you have to have enough plane wave that describe your system, so be careful. And the same as other DFT method, the overriding problem about LDA or GTA, the approximation in exchange correlation function. And the band gap also underestimated like other DFT method. And for plane wave, the vacuum region is included in the calculation. So if you have bigger size, it would take you more or longer time